On our next example, we look at how to interpret the graph of a function so that we can pick out some of its key characteristics. Let's look at example 10. This says use the function f, and see it was y equals f of x is how that thing was named, pictured, to answer the questions. So on part A, it says determine f at -2. So what's the value of our function at -2? Y'all, part A is asking, what is y when x is a -2? So we're looking right here. When x is -2, the y value is 1. So our function at -2 is equal to 1. What's on part B? What's our function value when x is 3? When x is 3, what is y? Or what is our function value at 3? Okay, so our function value at 3, which is right here, is going to be this point, which is also 3. So our function evaluated at 3 is equal to 3. Okay? All right, on part C, it says find all x for which f of x equals 1. Okay? Oh, sorry, that says -1. So basically, we're going to say when y takes on a value of -1, where does that happen for x? Well, that doesn't happen. Our function values are not going to be equal to -1 anywhere on this one. So we would say something along the lines of none. Okay? On part D, however, let me clean up my graph a little bit. On part D, it says find all x for which f of x equals a -4. All right, well, that's going to happen, f of x equals -4, for these values of x that go from 0 to 2. Now, because of the closed circle there at 0, -4, okay, we're going to say include 0, but up to 2, okay? That is an interval notation. Now, if we wanted to say all the x values that are greater than or equal to 0, but also less than 2, those values for x have a y function value of -4. Okay? All right, now in part E, it says to determine the x-intercept or intercepts if there's more than one. So on part E, where does the graph cross the x-axis, or at least touch the x-axis? We only have one x-intercept, and that is at the point -1, 0. Okay? Determine the y-intercept or intercepts. You know, there's just going to be one y-intercept if it is a function. And I'll tell you what, it's not here at 0, 1 because of the open circle. Okay? Here at 0, -4 because of the closed circle, that is our y-intercept. Okay? All right, I'm going to clean this up again. Then we'll discuss what is the domain of our function. Remember, the domain of our function was the set of all x values for which the function was defined. Or I like to say where we have action occurring for our x values. And because of this arrow right up here, you know this is going to keep on going up and to the left. And so we have x values defined for values of x that are less than 0. And because of this point down here at 0, -4, we have function values or x values also in our domain, and also in between 0 and 2. And because of this closed circle at 2, 2, we have action occurring at 2 and on. So for our domain, I'm going to say all of it, all of that, all reals, okay? We can say all real numbers or all reals, Or we can say everything from negative infinity to positive infinity. Or in interval notation, we could say the set of all x values. I said that was interval notation. That's not. This is set builder notation. It's the set of all x values such that x is an element of the real numbers. That's fun. Okay? Now let's determine the range of our function. For the range of our function, we don't have anything going on until we get to -4. And then we don't have anything going on in between -4 until we get to 0, okay? And then we have values for y occurring because of this leg of the parabola all the way through here, and because over here also all the rest of the way. So for our range, we're going to say that it's going to be at -4. Okay? Let's see. We might just say, put the -4. Okay? And then union that with values of our function that are greater than 0. Okay? And it could also be equal to 0, therefore the brackets. So stuff from 0 to positive infinity. Okay? There we go. Let's fill in our blanks for our concept connections. Number 1 says a set of ordered pairs x, y is called a blank in x and y. The set of x values in the relation is called the blank of the relation. The set of blank values is called the range. All right, well, if you read on to the second sentence, it tells you what this should be. Okay, a set of ordered pairs x, y is called a relation in x and y. The set of x values in the relation is called the domain. And the set of y values is called the range. Now, number 2, it says, given a function defined by y equals f of x, the statement f evaluated at 2 equals 4, or the value of our function at 2 is 4, is equivalent to what ordered pair? Remember, this is your x value, so 2, 4. Given a function defined by y equals f of x, to find the blank intercept, evaluate f at 0. So basically this is saying let x be 0. When we do that, we find the y-intercept. On number 4, it says given a function defined by y equals f of x, to find the x-intercept, substitute 0 for our f of x or the y, however it's expressed, and solve for x. All right, given this rational function, number 5, given the rational function f of x equals x plus 1 over x plus 5, the domain is restricted so that the denominator isn't 0. Okay, and a -5 value for x would make that denominator be 0. That'd be bad. Number 6, given g of x equals the square root of x minus 5, the domain is restricted so that, okay, remember with the square root, we take that radicand of x minus 5 and we say you better stay greater than or equal to 0. Then you can be in our domain. Add 5 to both sides of this. And the domain is the set of all x values that are greater than or equal to 5. That's an ugly 5. I'm going to do better. 5. There we go. All right, number 7. Consider a relation that defines the height y of a tree for a given time t after it is planted. Does this relation define y as a function of t? Basically, we want to see if for any given time t, any time, can there be 2 different heights of that tree? Well, no. Okay? For each time So this is yes, it is a function. Okay? Because for a given time t, there cannot be, for a given time t, that only corresponds with one height value. Okay, another way that we could say that is there cannot be more than one height. And then we let that be y. Okay. On number 8, says consider a relation that defines a time y during the course of a year when the temperature T in Fort Collins, Colorado is 70 degrees. Does this relation define y as a function of T? So what we want to know is are there different times throughout the year in Fort Collins, Colorado when the temperature reaches 70 degrees? Sure. There's more than one time of the year when the temperature is 70 degrees. It might happen on May 1st, and then it might happen again on May 15th, and then it might happen again, so on and so forth. So this is no, because there are numerous times in the year when the temperature is 70 degrees. There are numerous times in the year when the temperature is equal to 70 degrees. Okay? One other thing to think about these is like if it asks, does the relation define y as a function of t? You need to look at t temperature values, comma y, which means times of years, and you need to see if a temperature of 70 degrees can happen for multiple times of the year, and we decided yes it could. That's why this one was not a function. Whereas on number 7 it says, does this relation define y as a function of t? Okay, so we want to see t is the time after it is planted. Okay, so at a particular time after it is planted, could it be several different heights at that particular time? No, that couldn't happen. For each time after it's planted, that corresponds to one and only one height of the tree. That's why that one was a function. All right, time to do your 2.3 homework. Once again, if you're ever going to be graphing, do that on graph paper.